Hey guys, welcome to today's Leetcode contest. It's a weekly contest, number 410. Let's get straight into it. Um, yes, I was able to solve all four problems with, I think, 12 or 10 minutes left. And it was a pretty good contest. I'll go through the third and the fourth problems first, and then I'll upload new videos for the first two problems. So directly jumping to the third problem, um, count of monotonic pairs. Okay, so here let me explain the statement. We are given an array of size n, and we need to find two arrays which contain non-negative integers such that the sum of element at these arrays is equal to the element of the given array, and these two conditions are met. Basically, array 1, which you want to find, is non-decreasing, and array 2 is non-increasing. And since there can be a lot of such arrays, you want to find how many such arrays satisfy the condition. So this is it's like a pretty straightforward problem to understand. Nothing much going on here. Let me check if I'm recording. Yep, I am. Yeah. So let's say, for example, 2, 3, 2, and the good pairs are this. So if you had 0 and 2, you get this 2. If you had this 1 and 2, you get this 3. And if you get this 1 and this 1, you get 2. And this is a non-decreasing array, and this is a non-increasing array. So it's like sorted in some ascending order. This is in descending order. And if you verify all these examples, you'll find that there are four such arrays, pairs of arrays which satisfy this condition. And for this, it's 126. So yeah, it's a pretty strange number, but we want to find how to solve this basically. Yeah. So it's a TP based solution. Since the constraints on n is up to 2000 and the numbers can go up to 50, we can do this. Let's say my dp of I, j, k is the number of pairs of arrays till I, okay, till index I. Basically I belongs from 0 to n minus 1, such that your array 1 of I is j, and array 2 of I is k. Okay, this is your dp. Now the third condition says this, that your j plus k should be nums of I. So essentially j plus k is, I'll just say n of I. That means k is all, basically you can fix k to be n of I minus j. Okay, so that's what we do here. Just fix that k, and essentially you want to calculate dp of I. If you put j here, then in array 2 you have to put n of I minus j. So how to calculate this? So this is nothing but a double summation over something in the previous state. So let's say you go to the previous state on I minus 1, and let's say you put k1 over there and k2 over there. So k1 goes to array 1 of I minus 1, and similarly k2 goes to array 2 of I minus 1. Okay, your k1, so since this now in array 1, your array 1 will look like this. Sorry, your array 1 will look like this. It will have some j at its ith index, and all the elements that are over here will be less than equal to j, right? So your k1 is at I minus 1 position. Here you put k1. So your k1 is also less than equal to j, right? So yeah, so that's what you will do here. k1 would go from 0 because the smallest number is that's possible is non-negative, which is 0, and it will go up till j. Okay. And k2, what about k2? So k2 will essentially belong to some valid set. And how do you find this valid set? It's essentially a restricted set, and what you will do to find k2 is that now k2, you know that k2 is n of I minus 1 minus j, sorry, minus k1, right? This is your k2, which is fixed always. And the only condition that you need to apply is that this number should be greater than or equal to n of I minus j. This is the condition that you need to apply. Because you put n of I minus j, so your array 2 is now like this. You put n of I minus j over here at index I, and in index I minus 1. So now all of these numbers should be greater than or equal to n of I minus j, right? Because this is non-increasing. We have to make this array non-increasing. So that's why here I will put n of I minus 1 minus k1, right? Because here if I put k1 in array 1 and the sum of these two should be equal to n of I minus 1, then obviously I'll put this number, similar to what we saw in the index at the index I. So then this condition should hold because n of I minus 1 minus k1 should be greater than or equal to n of I minus j to make it non-increasing. So this is condition number 1, this is the condition number 2. And your valid set will look like that, like this, okay? And yeah, that's pretty much it. Complexity for this would be, so since we are fixing k1, so since we are fixing k2, k2 is fixed, right? It can be derived from k1. The complexity would become O of n cube. Sorry, O of n into your max square. So max is up till 50. Max is basically the maximum number that can occur in the array 1, the first array and the second array. Yeah, so let's go into the implementation. I think it will clear. I think this is the equation. Yeah, this is what you have to solve. That's what I'm doing here. This is the first variable. I'm having a dp of size n k1 k2, okay? And then this is the initial condition that you iterate over all the i's, all the j's on the first position, and basically I am initializing the initial state over here. And if this I plus j is nums of 0, then set this guy to 1. And that's what I'm doing here as well. Now I'm iterating from 1 to n minus 1 because I already calculated the initial state, okay? And now your j would go from 0 to nums of I, right? So basically this guy will go from 0 to nums of I because that's the maximum value you can put at the jth position. Sorry, at the ith position in array 1, the maximum value you can put is nums of I, right? Here you can put nums of I only. It cannot exceed nums of I because then you would need a negative number at the other place. And your k1 would go from 0 to obviously nums of I minus 1 plus 1, right? Yeah, it can go up till j, so that's how I put a breaking condition over here. If k1 is greater, like exceeding j, then break, and if else, like if this condition is met, basically this condition that we discussed, this one, then just increment that answer. So put j here, nums of I minus j here, and then increment that much answer from the dp. So put k1 and the k2 which is corresponding to k1, just add that. So yeah, that's this loop. And then if you do this dp, at the end you have to calculate the answer also. So similar to what you did in the initial state, you just do it at the final state. You had all the answers which have I and j, such that I plus j is the last number, and just add the dp to the answer, because we saw that it's a number of pairs till I, right? So when you want to calculate till n minus 1, you'll just do n minus 1 ij, just do a summation over these such that I plus j is n of nums of n minus 1. Yeah, and this will return the answer. That's pretty much it. Okay, so coming to the fourth problem. So now here's where things get tricky. Your number of pairs remain 2000. Sorry, number of numbers remain 2000, but your numbers can go up till 1000. So earlier what we did with this guy, this was like so this was like 2000, and this was like 50 and 50, and the complexity was of 2000 into 2500, which we just managed to pass in. This passes in time because it's of order 10 raised to I think 8, which passes. But if you put 1000 and 1000 here, there's no way it's going to pass. So we cannot do this dp, and we have to think of something else. So now, to optimize this, what you will do is that to optimize this, dp of I, j, k. So we can get rid of this k, because we always know that it's going to be derived from k1, basically from array 1, right? So let's get rid of this guy. Okay, and now you can rewrite this equation as sigma k1 equals to 0 till j. Okay, and just put dp of I minus 1 comma k1. This is the equation that you want to solve, but this is like kind of this is incomplete. Your k2 would be obviously k2 would be ni minus 1 minus k1, right? And we also saw that your ni minus 1 minus k1 should be greater than or equal to ni minus j from the previous condition, right? What that implies is that your ni minus 1 minus ni plus j should be greater than or equal to k1. So now we have a bound on k1, on how much can we iterate on k1. Okay, and yeah, we have this bound here, but your k1 should also be less than or equal to ni minus 1, right? This is the other bound that we have, and the third bound we have is that k1 should be less than or equal to j. Okay, this is coming from here. So at I you put j, this is your array 1. At I minus 1 you can always only put a number which is less than or equal to j, right? This comes from there. This comes from the fact that since your nums has ni minus 1 over here, your k1 can at max be ni minus 1. Okay, and this comes from this fact, this condition comes from this fact here that we just proved in problem number 3. Yeah, so now what you'll do is you will take like the minimum of all these values. Just take the minimum of all these. That will be your maximum range. Minimum of range 1, range 2, range 3. This is your range 1, range 2, range 3, and 0 obviously is the minimum value, and this is the maximum value that k1 can take. So k1 will belong from this to this range. Okay, And as a matter of fact, your j belongs from 0 till nums of I, right? Yeah, your j belongs from 0 to nums of I. And so you can basically ignore this range, ignore this, because your j belongs from 0 to ni. So if I put ni over here, which is the maximum value here, then it will become ni minus 1, and all the other values will be less than ni minus 1. So when I take the minimum of these two, this guy will always win. So I only need to take the minimum of this one and this one. So like, that's pretty much the idea. Let me jump to the code. So that's what I've done. I eliminated the third variable and put 1001 till here. And yeah, this is also pretty important. One more optimization is, like, this guy solves in O of n square, but in order to calculate it, you require one more O of like n. So complexity would be O of like n into max square. So this is O of max, this is O of n into max, right? Because you're still running one more loop over here. So complexity is still O of n into max square, and this will give you TLE. So now how do you optimize this? So notice that this is nothing but going to some previous state and doing some prefix sum on it. So let's say you are like index I in this is your DP table, and you are at index j here. Okay, you go to I minus 1, and essentially you want to calculate your k1 belongs from some 0 to some range r. Let's say this guy is r. Basically it's like the minimum of these two guys that we just saw. Let's say that is r. So 0 till r. So dp of I comma j, this is your dp of I comma j, and this is your prefix sum. Let's say this guy is r. Okay, and obviously, sorry, my bad, it will be less than j. Your r will always be less than j, right? Because it follows from this third condition. So this is, let's say, r. My r is some prefix sum till that guy, and what you're doing is just adding this guy here, and this one you can always pre-calculate using prefix sums from the previous state. So that's what my code does. 0 comma I is always going to 1. This is my initial state that I'm doing, and this is always going to be 1, because if you put I at array 1, then you can always put nums of 0 minus I. So that's why this is going to be 1. And then you do a prefix sum on this DP. Okay, so prefix sum of I equals to previous prefix sum plus the current value. And this is the minimum condition I was talking about. The first one is j plus 1. Basically, like, yeah, I mean, I was just running a loop in the previous loop condition, that's why I do j plus 1 minus 1, but you can also write like this, j like this will also work. And yeah, that's pretty much it. Just calculate the range r and just do the prefix sum on it, just add that prefix value, and then you again reset that prefix sum and recalculate the prefix sum for that particular line. So now after you're done calculating this, you have to calculate the prefix sum for this in order to get ready for I plus 1 state, right? To calculate the I plus 1 state. That's why you have to run a loop here also. So these 3 loops run parallelly. It's like first this loop completes, then sequentially, I mean, but it's like within the same, at the same level. So it's like the complexity is still n into max, which is n into 1000. And in order to add all this, you just add the answer to the DP. Yeah, that's pretty much it. If I run code, then submit. Yep, accepted. Yeah, so that was about the video. Hope you guys enjoyed the solutions, and thanks for watching. Bye.